Right. So average distance from Earth to the Moon, 3.84402 times 10 to the 8th meters. What is the period of the Moon's orbit? Now we have derived an equation of belief that could be a shortcut, but let's sort of do it from scratch. So let's say you're faced with this problem. What's the first step?
So that number is the radius of the moon's orbit?
Yes.
Find the circumference?
Okay, we could. There's a step I would do before that, but.
Draw it.
Pardon?
Draw it.
Yep, that's the first thing I would do. Earth.
Moon.
Finding circumference just because you feel like you'll eventually need it?
Yeah.
Okay. What's the formula for circumference?
2 pi r.
It's one of those two.
2 pi r.
Yes. Remember, circumference is a linear. It is basically it's the distance along a line. So there's only one r in it. Like a radius, it's only distance along a line. So that becomes 2 pi times 3.84402 times 10 to the 8th meters. So what is that?
.41.
4-1?
Meters.
All right. It is possible to solve this problem without actually knowing that number, but it is also possible to solve it with knowing that number. Now what? We've done loads of problems like this. What's the first step of pretty much every problem we've done since chapter 4?
Force.
Yes, so force diagram. What are the forces acting on the moon?
Earth gravity.
Now there is a force of gravity acting back on the Earth, but not relevant to the problem. What other forces are acting on the moon?
There's no normal force not touching anything.
Okay, so normal's out. So we'll go down our checklist here. So we did force of gravity. That's a G there. No normal force, okay.
Acceleration go down.
Acceleration would be down. That's the next step after this, but
No tension,
There's
no
no
friction.
no hand of God moving that moon around. All right, so we're done. A very simple force diagram right there. We've already established the direction of acceleration. What's next?
So, coordinate chart.
All right, so coordinate system or coordinate axes. So what do you want to do?
I have down.
Okay. Since it's only a one-dimensional problem, we can get away. We don't have to use I hat if we don't want to. We could just say down is positive.
No.
But you could also say down is I hat. So either way. What's next?
No decomposition.
Okay. Then what's next?
Equation.
Okay. What's the equation?
It's gonna be
E equals acceleration.
All right, what did, I think I missed a letter.
FG was.
Okay. I didn't hear the F. It was up. Oh, sorry. FG is equal to MA sub C. How do you know it's sub C here? Okay, what's the defining characteristic of centripetal motion? I heard somebody whisper it.
it's moving in a circle.
Yes. All right. And at constant speed. If it were moving around the Earth and speeding up, then you would still have centripetal acceleration, but there would also be a tangential acceleration component also. That's not what we're doing right here, though. All right, so we are assuming circular orbit, that the orbit stays relatively the same, so we're not dealing with ellipse or anything like that. What comes after the equation? Okay, so for what do we have a formula? Okay. So what's the formula for the gravitational force? We don't, if we're doing that, that's m little g. We don't know the acceleration due to gravity. So that would be a very difficult way of going about it. Or if we wanted to derive it, we need to know the other formula, the more generalized formula. Oh, and this is mass of moon.
And the V squared over R.
That's over here. So we have mass of moon, v squared over r.
We use the G M1, M2 over R squared.
That's the one. Big G, mass of the Earth, mass of the moon, over r squared. We actually have one other formula that we can do at this point. Because ultimately we're trying to find the period of the orbit. What exactly do I mean by period?
How many times it goes around a Cleveland circuit?
Say the first part again?
How many times it goes around?
Not how many times it goes
No,
around.
not how far, how long it takes to complete a circuit.
Okay, so the time it takes. I don't know if I just misheard or. So the period is the time it takes to go around. So we're trying to find period, so the symbol for it is a capital T. And that's not in our formula yet. So where does period show up in the formula?
NT, just like times NT.
Oh, we're just gonna multiply it?
Oh, I'm getting tricked because like every time you'll do like a reference and then it's plus two and pi, but I'm getting, that's what I'm
Yeah,
getting.
those. Yeah, we're not adding just another 2 pi radians. It's a time it takes to go around. Where does that show up? Or speed, actually. What's speed have to do with period?
Change in distance over change in time.
So speed is change in distance over change in time. And the distance is the circumference. And the time is the period. So this is why I said before, we didn't actually have to know the value of 2 pi r. We can just leave it as 2 pi r and then work through it. Or if you want to, you can plug that in for 2 pi r if you want. It depends on at what point you want to stick numbers in. I'm going to hold off on that for the moment. So this becomes mass of the moon times 2 pi r over t squared over d. So G, mass of the Earth, mass of the moon, over the orbital radius squared equals mass of the moon 4 pi squared r squared over t cubed. And we're solving for t. Oops, messed up there. That's an r right there. That's my mistake. Over r t squared. What can we get rid of?
Mass moment.
Yes. Common factors. What else can we get rid of? All right, so I heard r.
R squared.
We can't get rid of r squared because it's the denominator on this side and on the numerator on this side, but we can get rid of that r and one of those r's.
I thought we were cross multiplying. I thought you did it from the numerator to the denominator.
When you cross multiply, yes, but not when you're canceling.
Okay.
Across an equal sign, you have to cancel tops or cancel bottoms. You can't cancel across the diagonal.
Okay.
Or if you do, you get the NHMW, which is not how math works. All right, so from this one right here, let's do some cross multiplying. So we got G mass of the Earth times the period squared equals 4 pi squared r cubed. Now what?
Just plug in.
Let's do one. Let's isolate period first. Yeah. So we want t by itself, so we have to get rid of the things attached to it by undoing how they're attached. And so we're left with t squared equals 4 pi squared r cubed over g mass of the Earth. Let's go ahead and do the numbers at this point. So we get 4 pi squared times 3.84402 times 10 to the 8 meters cubed divided by 6.67 times 10 to the negative 11. Since we're doing units there, that's Newton meter squared per kilogram squared times mass of the Earth, 5.98 times 10 to the 24th kilograms.
I have a question. Why isn't the radius, the distance plus the radius of the Earth? Because
Sorry, why is this?
yeah, like I don't know. Because it's the distance from the moon to the Earth, right? So I don't. Never mind.
You feel like it should be surface to surface?
Oh, is it not?
It's center to center.
Oh, okay, that makes sense.
Okay, is that clear enough? Okay. Yeah, when especially if this r right here were surface to surface, as r gets smaller, this fraction gets bigger. That's going to be true regardless. But that means if it's surface to surface, that means if you went outside and touched the ground, you'd be stuck because the force would be infinitely large. So fortunately, it is center to center.
Is that negative 11 or negative 4?
That's a negative 11.
Okay.
Hopefully, it looks more like an 11 now. And so we get
I got 5.62 times 10 to the 12.
Now, this is not our final answer, but in this intermediate answer, what are the units?
Per second.
I heard vocalization over there.
Seconds.
No.
Meters.
Pardon?
Meters.
Nope.
In times n squared over kilograms. No.
You're trying to do the based on the units here? You could do it that way. But think about what we just solved for.
T to the first.
Oh, seconds squared.
Yes, second squared. Because this is the period squared. All right, therefore, the period is
(2.37 times 10 to the 6 seconds.
So the question right now is this correct? Well, let's get it in something that we're more familiar with in terms of how long it takes the moon to go around the Earth. Let's put it into days. So I need to convert this into days, and I know that there are 86,400 seconds in a day. The seconds would cancel out. And how many days would this be?
27.42 or 44.
And that's roughly how long it takes. That's from new moon to new moon or full moon to full moon is roughly a month. Questions on this glorious problem? Yes, I know. You're stunned by the awesomeness of it. Well, when you come off of the physics high, and you can think of some questions, please feel free to ask. We've covered all the material, as one would hope, especially since the test is next week. Any questions concerning the test next week?
So for G, with the two masses, like when would you instinctively know like when to use them? Because that's the thing. Like I don't instinctively think to use those. I just get to F equals ma. I'm like, okay, that's what I'm working with.
So when do you know to use this?
Right.
That specific formula? All right, so force due to gravity, we have two formulas.
Mm-hmm.
We have mg, and then we have this one.
Right.
So this is the much more generalized one. Mg is specific to if you're near the surface of a planet.
Oh, okay.
So, at least that's when it's easiest to use.
Right.
So in a case like this, once you get off the surface of a planet, then you can pretty much be sure that's the one that you're going to be using.
Got it. And then it's just moving around, map manipulation to get the rest of it.
Yeah, and so recognize you're off planet, so we're dealing with that.
Right.
And it's circular motion, so
Okay.
you got that, and so then it becomes math manipulation after that.
Okay.
Physics tells us this, officially math tells us that,
Mhm.
and then it's what are we actually trying to find?
So you'll give us like the big G values and like N, or whatever specific to the column.
Yeah, G, the big G is the gravitational constant, so it would be top of the first page. It, I think I give it to you, 6.67 times 10 to the negative 11th is fine, but I think so there's some tests out there where I wrote it out to several more decimal places, just for fun. Don't feel like you have to use them all, just 6.67 is sufficient. Other questions or follow-up?
But what's that units, with the negative 11 power?
Newton meter squared per kilogram squared. It's set up so that the units of this are that if these are both in kilograms, kilograms would cancel. That's why it's on the bottom there.
Okay.
And if this is in meters, it would cancel out with the meter squared there, and you'll have the newtons.
Mm.
This unit is specifically designed to make the units work out in whatever unit system you're using.
Okay.
So if you were using in the CGS system where forces in dynes, then it would be a different number, but it would be dyne centimeter squared per gram squared.
Got it.
Fortunately, they stopped using dynes well before we got here.
Oh, okay.
Okay. within my lifetime, but probably easy for most of your lifetimes. Pardon?
Do you say fortunately?
Yeah, fortunately.
Oh, okay.
What
Dine's just not a convenient one.
What are they called?
Dine, D,
Yeah,
dine. Not the kind of eating, but dine. I assume it comes from some variation of the word dynamic or something like that, or the same root. All right, other questions?
And because you knew you looked from here, you knew to use circumference, you know that was gonna something we're gonna have to figure out.
Yeah, I know that the speed for circular orbit is distance over time, as Keelan had laid out before, and the circumference is 2 pi r. So I knew it was gonna pop up.
Could have we used omega, like the angular velocities or this one, or?
You could, if you went omega route, so this is m massive moon omega squared over r. Omega is, so this becomes massive moon omega over, omega would be 2 pi over the period squared. Oh, it's not over r, omega squared r. Yeah, you could have gone that route too.
Okay.
It actually, I don't know, is that simpler? If you're dealing with one less variable, but that variable canceled out anyway.
Well, since we're talking about angular speed, and that's the first thing I was kind of thinking about, then you did that one, I was like, okay, I wasn't ready for that one.
Yeah, I'm just so used to doing the v squared over r, that's my go-to.
That makes sense.
Other questions on this or the test, or?
If you ever get to a problem and you have two unknowns, what is like the best way to go about like solving the problem?
All right, so if you have two unknowns and you have, what, one equation? If you have two unknowns and one equation, then either there's clues in the problem where you can ignore one of them, like we did earlier in one of the sample, one of the homework problems, or two, you missed an equation somewhere. And so with something like this, it's a one-dimensional problem, so I know I'm gonna have one equation.
Yeah, I'm not just other problems.
Yeah, I'm not quite sure I could generalize it really more than what I've already said. So I guess for projectile motion problems, you know, say like on a test or something, don't forget you have horizontal and vertical. Which is pretty much true with a lot of stuff we have here, where you've got, you know, direction of acceleration and perpendicular to that, so you got two equations for a lot of things.
Could we go over another projectile motion problem?
Okay.
You ready? Like quick.
Just for fun?
Yeah, just for fun.
All right, so this is the basic setup here. What do you want to find?
Acceleration.
You want to find acceleration?
Good.
All right, so we're on some strange planet. We don't know acceleration.
Jupiter.
Well, then all we have to do is look it up.
Just do Earth.
Yeah. We know that.
All right, so we know, so if we're doing Earth, the answer is around 9.8 meters per second squared. Down.
Just do Jupiter's moon. Whatever.
All right, so we're on some strange planet. I launched this at, say, 50 meters per second at an angle of, let's go to the classic 37 degrees. So we can set up a 3, 4, 5 triangle here. Gonna go. Let's see, if we're trying to find G, it seems like we do need to know some more information here, if I don't get too much. See if I know that. I think all I have to do is just tell you this value here. Let's make it more exciting. I'll tell you this value and not tell you that one. Let's make this 100 meters. I might at some point go, oh, we do need to know that, but I think that's all we need to know right there. So let's do this from a force point of view. Once it's in the air, what's the direction of acceleration?
Repeat that?
Once the object is in the air, what is the direction of acceleration? I heard down. What are the forces acting on it once it's in the air? All right, there we're done. So we set up a coordinate system. Up or positive or down positive? I heard down first. All right, so we'll make that down, that's positive. There is motion in that direction, so we'll make that my I and J. Now ordinarily, we'd be solving for acceleration doing forces, but we don't know the mass of the object, so we really can't do it that way. This now bleeds into a projectile motion problem. But we'll have an I equation and a J equation. But let's figure out the quantities. We got delta x, we have initial velocity, final velocity, acceleration, and time. This is what we're trying to find right here. For the lack of anything better, why don't we call this G? All right, so what do we know?
I displacement,
Which is?
100 meters.
All right, what else do we know?
I would be 50.
No.
No, both of them, but we have to break it up.
All right, we do have to break it up. So I have 50 meters per second at 37 degrees,
I would be 50 cosine 37,
which is about 40.
and then that would be 50 sine 37 degrees.
And it's about 30. I picked 37 degrees for a reason. So we get 3-4-5 triangle. It's gonna be a little bit off. If I ever give you, there's a 36.8 and I give you a whole bunch of digits there, that's so that it actually comes out really nicely. 37 degrees is just the lazy man's version of what I do in some of the other problems.
So, for one, the final velocity should be the same as initial velocity?
For which one?
I'm trying to remember which one.
Horizontal.
Yeah. Yeah,
Why?
that's horizontal.
Because there's no force acting on
Therefore,
the velocity will remain constant.
therefore,
The acceleration is zero.
there we go. All right, so we have 0 meters per second squared right there. Initial velocity, I direction, is 40 meters per second. What is my initial velocity in the J direction? Yes, please don't forget the negative sign. We said down was positive, so this is negative 30 meters per second. If we made that positive, we basically would be changing the problem to shooting it up at 37 degrees to shooting it down at an angle at 37 degrees. And that's what we know.
No final velocity for I.
Oh, okay.
Now we use a find time for both of them?
Yep. So how would we find time?
We use a first figure equation. Displacement equals full velocity F minus velocity,
That's one.
no, plus velocity F, plus velocity I over 2 times time.
All right, that works because we know that they are the same. Or you could have also used, what's the other one?
Plus 1/2 AP.
Yes, I've noticed a lot of people, and I can't remember if it's this class or the other class or a combination of the two, people who wrote down parts of formulas, not the whole thing. It's delta x VIT, sometimes people left the t off. Sometimes they confused their t and the plus sign and suddenly one of them disappeared. Plus 1/2 AT squared, too many people dropped the square here. And some will drop the 1/2. Either of these equations works for the horizontal.
Use the first one, so I don't have to do the other one.
All right, you still wouldn't because acceleration 0, so that drops out.
Right.
So either one, you get the same place. So we have 100 is equal to 40t. And doing the fancy math, 2.5 somethings.
Yeah.
Yes. So 2.5 seconds and 2.5 seconds is the same in both directions. And so we have that. Yeah, I might have to give you that vertical distance.
There's no way you can use the angles to kind of trig your way up at that, right?
Yeah, I don't think so. Because ultimately, how long it's in the air depends on the vertical. Horizontal just picks up on it and uses the same time, but vertical determines how long it's in the air, and how long it's in the air really depends on G and how high a cliff it is. So, all right, so let's come up with a number here. Let's make it 21 meters. So what is the displacement in the vertical direction? Positive or negative? Yes, it is. All right, so now what do we need in order to find G? Oh, yes.
Why is it not negative? Because it's starting from the highest and oh, there you go.
That's why it's important to write that down early, just so that you keep track of it. All right. So what formula should we use?
I'm used to use the first
Same
one.
one,
We're solving for acceleration, so that's probably not gonna help us a lot.
the same one you just used.
This one right here? All right, so we get 21 equals negative 30 times 2.5 plus 1/2 G times 2.5 squared. So 21 equals, let's see, 67, negative 75 plus, that's 6.25, so 3.125 G. Add 75 to both sides. So I got 3.125 G equals 96.